Today we're going to do an introduction to DevOps. DevOps is a term that is out in industry in many situations. You hear it a lot, but a lot of people aren't familiar with what it is. It's a funny term. It may not even be the best term to describe what we want to talk about. Myself, I would tend to call it modern software engineering. But DevOps is the term that's out there, so it's a term we're going to use. I'm going to give you an explanation of how the term came about. One of the principles that I've adopted when I try to teach something comes from R.G. Collingwood, who has said that to really know something, you have to know the history of the thing. We don't understand, for instance, the full meaning of a philosophical position unless we understand what earlier philosophical positions that position was an answer to. So, similarly, we won't really understand what DevOps is unless we understand DevOps' solution to some problems. If we don't know what those problems are that DevOps was solving, we don't really understand DevOps. So, we're going to go back. To beginning of the 20th century. And beginning of the 20th century, what did we see? We saw the rise of assembly line manufacturing, where people are in a line. Each person is doing one simple job. I'm modeling this after an assembly line I actually worked in, where I was putting lids on jars of skin cream, and sat there all day and screwed the lids on jars of skin cream. There was a number of ideas floating around in business thinking, social thinking in general. One of the things that was going on was that there were certain very bright guys, right? So this is his academic cap, right? So here's this guy, he had a PhD. And what he does is he plans the entire process and directs everything these people are going to be doing on the assembly line. The people on the assembly line are not expected to be thinking, they're expected to be screwing the lids on jars, or tightening a bolt on a tire, or attaching a steering wheel to a car. We had movements like Taylorism, where this business thinker Taylor explicitly set the goal that all knowledge and planning, the knowledge and planning that used to be done by craft workers on the job, so skilled carpenters, skilled masons, skilled weavers, and so forth, skilled bakers, right? So we could make bread on an assembly line like this. That knowledge that the workers had would all go upstairs into the planning office and the engineering office. And the workers were essentially turned into a capital good. They were turned into a kind of flexible machine. The only reason you really needed them was that in 1910, 1920, it was too hard to build a machine that screwed the lids on jars. Otherwise, you just do away with the workers and have a factory floor entirely of machines. And we've seen that happen in many cases now. So this assembly line model gets moved into the world of software. So if this is the way, this is the modern way to do business. If we're going to be making software, well, we want to do it this modern way, right? And so what we get is the waterfall model. We're giving a sketch of the waterfall model. There were people who did this much better than others. Sometimes it produced good results. But the general idea of the waterfall model was this. There were and these were the only people who talked to the customer. And they produced a big requirements document that flowed down to designers who set out some technical specs, and those get passed to programmers, and the programmers, they made code, and this went to testers, and finally, at the end of this, things would flow back to the customer. The programmers in this model were very much analogous to the factory floor workers. They were someone who could take these technical specs and type them out in COBOL or Fortran or whatever the language was. And they really were not expected to be thinking of anything other than what's the right line of COBOL, because the requirements were supposed to be complete. The analysts who had the same role as the PhD engineering planner did in our factory had captured everything about the system. This document was complete. They knew everything that was going to be needed, and now we just needed to pass this down. These people didn't mess with the requirements at all. They just said, well, here we're going to use this piece of technology to implement this part of it and this piece here. They passed this to the programmers. They were able to turn it into code. They passed that on to the testers, and once it passed testing, the customer gets the product. This model had sometimes produced good results, or else no one ever would have used it, right? But it had severe problems. It often resulted in enormous delays in the delivery of software. It would, many times the software simply never got delivered. The air traffic control system, at some point a decade ago, I read that they were the largest user of vacuum tubes in the world, because they had multiple projects run like this to replace the air traffic control system, and they had all failed, never produced a working product. So they were still using their vacuum tube computers on which the first software had run, and they couldn't get rid of it because every attempt to replace the software failed. What goes wrong here? Well, it's very difficult to get everything into this document, and that's for multiple reasons. This conversation is not error and trouble-free. Often the users are vague about what they really need. They don't know what they need until they see it. They say they need X, and once they see X, they say, oh my, that's totally wrong. I guess what I really needed was Y. The analyst can misunderstand these things, but furthermore, it's often, we discover things in the process of building a system. So once we start building something, it can easily be the case that we realize this, wow, we didn't need to build it this way at all. Now that I actually have it and have my hands on it, I see that this could have been much simpler. Or we missed a crucial part that I just didn't think of at the point I was talking to you. So these were almost never actually complete, like they should have been in theory. Working with incomplete requirements, the technical specifications, of course, couldn't be complete. But also, these people may not have known exactly the limits of the programming languages that the programmers knew, better ways to do something. And while the system is being built, new things can come out. A version of the software you're working with becomes defunct. The company buys a new computer and the thing you were going to run doesn't even run on it. So changes happen here. This step, code, the step between the programmers and testers was often a disaster because this waterfall model went one step at a time. The testers never got the code until everything was done. And it was very common for the project to be almost done and it would go into testing. The testing would drag on for enormous lengths of time. There's a joke that the first 90% of a project is done in 90% of the time required, and the last 10% of the project takes the other 90% of the time required. And this was all too typical. So, what happened? We had these problems, and there were fixes. The fixes came from two main directions, and they give us two words for types of software development methods that became popular in the last 10 or 20 years. One direction that was quite important here was that at the same time people were doing this waterfall model, there was a group of brilliant software engineers at Bell Labs who were developing the Unix operating system, the C programming language, Make, awk, tools like this. And they introduced things, although they didn't call it this at the time, minimum viable products, incremental development, microservices. These are all things that are big in DevOps today. They all have their roots in the Unix development environment. There's a book with that name that could be regarded as an early DevOps book. So the people developing Unix did not say, let's write a complete operating system that has everything the users might ever need and then release it. They said, let's write a minimal operating system that lets us get up and running, start using it, and then we'll figure out what else we need. They delivered a minimum viable product, then they added to it incrementally with very frequent releases. They also broke up, rather than writing one monolithic operating system, they broke up the system and wrote a core, the kernel, and then a whole bunch of utilities surrounding it. So that, whereas earlier operating systems would have things like showing what files were present or what processes were present built right into the core of the operating system, Unix didn't do that. They had programs like LS and PS that were separate, essentially early microservices that did these things. So we have this flow from Unix into web development, and these are the roots of what are called the agile development movement. The other main branch of ideas, which were very similar in nature, came from Toyota and actually from the factory floor. Toyota was trying to compete with the large American car manufacturers and realized that they could not compete on volume. So someone like Ford is trying to drive down the price by making 10 million identical cars. The customer can have any color car they want so long as it's black, right? This is one of Henry Ford's principles. They would make 10 million steering wheels, and if the steering wheels weren't what the customers wanted, they would tell the car dealers, well, get them to want those steering wheels, huh? Because we got 10 million of them, we've got to get rid of them. Toyota said, we can't compete with the American companies on volume, but maybe we can compete by having a more intelligent factory floor and by being more flexible. And so they developed what's called lean manufacturing. For one thing, it's a pull system. Things get pulled through the production process by orders from the customer. So it was, rather than telling the car dealers what they had to sell, the manufacturing plant would ask the car dealers what the manufacturing plant should be making. In order to have this work, they had to make small batches. They couldn't make 1 million cars of one type because you might make 100 and find out that, well, only 100 customers wanted that. Now you have 9,999,990 cars that the customers don't want. So they learned to work in small batches, and they rejected the factory model of Taylorism and said, in order to gain this flexibility, we need to have all the workers' intelligence devoted to making their workstation flexible, to them being able to pull work from further down the line. So they're not overwhelmed, they're not creating waste at their workstation. And so they can tell us how to configure their work area for this flexibility. So rather than trying to turn the worker into a machine, Toyota very much was asking the worker to be an active, intelligent participant in the production process.
So I have a question.
Yes.
So, like you said, so I read somewhere that they encourage people, the workers, to like learn other stuff as well, other than what they're doing.
Absolutely.
So how did they were they asked to do something like, for let's say an example, like do this for 1 month? Like if you're making a steering, then just make the dashboard for 1 month and.
Yeah, you can move people around from task to task. This is an excellent way to broaden their knowledge. Why is this important? If you're going to be changing the steering wheel workstation in response to customer demands, the person at that workstation also needs to have an idea, how is that going to affect the dashboard workstation that comes before me? What do they need to do to prepare me to do this change and the workstation after me? So for the workers to respond intelligently to requests for change, the workers need a broader view. They can't think, I'm just the person who screws the cap on the jar. They have to have an idea of how is the jar filled? How is the label put on the jar? How do we check the jar further down the line?
And first one more thing that come out from this. So how did they manage to get some high quality product out of this? Suppose a person is he's mastered in making steering wheels, and if he is making dashboards for the next month, and then he's again making something else. So how would they become master?
That's where collaborative thinking would come in, I believe.
Yeah. So yeah, there is an advantage to specialization, right? Mm-hmm. So we can look. What is happening with the factory floor model is we have Adam Smith's principle of division of labor pushed to an extreme, right? So people do just a very simple single job. And there are advantages to pushing this away, but at a certain point, even Adam Smith recognized that the workers kind of shut down their mind, right? Mm-hmm. And you're not really getting any intelligent involvement for them because their task has become so small and specialized that they turn off their minds. So we need a balance. Mm-hmm. It's true, we don't want people running around. We can't have people spending 5 minutes doing C++ coding, yes, and 5 minutes doing testing, and 5 minutes bringing up web servers, and keep them going like that and expect that they're going to be skilled in any of those things. What we need is a generalizing specialist. So we have people develop a specialization and then gradually try to broaden their horizon so that from their specialization, they're a skilled Python programmer, works with Django backend, Okay, well now let's have you learn some testing so you can see how your code can be better written to be tested, right? Now let's look at how monitoring software works so that it's easier to monitor your code. Now let's take a look at automated build tools so that you see how to structure your code that we can build it easily. So we need specialists, but we need specialists who can
With a
take
holistic view of the things.
yeah, they can learn the broader view over time. So we have these two, lean and agile, become very popular in software development. And what happens is that people adopting these methods of developing software begin to be able to release software very rapidly. And with applications moving, no yawning, okay? With applications moving more and more to the web, we don't have to ship customers disks, right? We don't need to go to their mainframe and install the software. We just put the software on the web server. So not only could they develop software more rapidly, it was becoming increasingly easy to get it to the customer, right? We just update our own web server. We don't need to go to the customer's site or mail them something. So these technologies are allowing people to release software very quickly. There is a problem though. This is the development side of things. There was, in the same organizations that people are adopting lean and agile, there's the operations department. And operations, whereas the developers were saying these fast releases are great, we can get the customer features they need right away, they're getting value, we're satisfied because we know people are using the things we're writing. Operations, the general mindset was that releases are scary things and we want releases to happen as infrequently as possible. So maybe once a year you release a new version because the release is going to hurt a lot. It's going to mean the system crashes 20 times in the first 2 weeks that it's out. It's going to mean floods of customer complaints on the telephone. It's going to mean everyone in operations is getting woken up at 3 a.m. when their pager going off because, yeah, it crashed again. And so operations hated releases. They wanted to slow releases down, plan them out at long intervals, let the system stabilize for a long time before doing another release. Come in, we're giving a talk, but we have some people joining a little late here, so no worries, come on in. So operations did not like this at all. So we have a conflict. Operations wants to release one time per year, right? And development wants to release, let's say, one time per day. That's terrible conflict. This is a not unreasonable pace. There are companies like Amazon that actually are able to release software into production every 11 seconds throughout the day. So one time a day might seem unrealistic, but there are companies that achieve much higher rates of release than that. So what can we do? We have these people who want to push the software out faster. We have people who are going, no, it's too dangerous, it'll crash all the time, we're never going to sleep. These people, if you have a company that has some kind of semi-monopoly on something, they can push the software out at a slow pace a big investment bank, for instance, that has the right to buy treasuries right from the US government. They have a kind of locked-in source of profit in being able to do this. They can resist the urgency to update their software for the customers because they have this locked-in source of revenue. But for a company selling things on the internet, for instance, the company itself is going to take the side of the developers because there's another company that's releasing software, and now our competitor has this fancy new JavaScript feature. Why don't we have it? We're losing sales to them. We need to get it out there. So there's this conflict. There were people in operations who were wise enough to say the right way to resolve this conflict is not to keep resisting, but we need to become lean and agile, like development. And we need to look at the techniques they've adopted to get their releases this fast so that we can handle releases this fast. A fellow named Patrick Dubois was one of the operations people who had this insight, and he organized a conference to have developers and operations people come together and talk about this. He was thinking of a name to give it, and he said, well, it's development and operations. So, I don't know, this name seems kind of, I don't know, people will like this, but I'm going to call my conference DevOps. He didn't really intend to name a movement or a method of doing things. This is just a catchy name that he thought he'd use for his first conference. It caught on, and pretty soon other people were saying, well, we're going to have a DevOps conference just like Patrick Dubois did, and people started calling the methods by which operations was keeping up with lean and agile developers under the umbrella term DevOps. So what had to happen? What happened was we got a DevOps toolkit, as it were, a variety of types of tools that we use. But all of these tools exist with one purpose in mind, or I think it's best to understand them as serving this one purpose. What we want is we want a rapid life cycle where we go, the user tells development what they need. This is tested. So we have and deployed to the user, and this enables feedback that we use to drive the next round of development, what improvements we need, which we push through again. And if we go around this cycle rapidly, what we do is we accelerate the learning pace of the organization. Rather than a waterfall project where, so let's say this cycle happens once per day, one time per day. Every day we have an opportunity to get new user feedback, as opposed to a waterfall cycle where we might program for 2 years and then ship something to the user. Well, maybe we went off track in week 2. We don't find out for 102 more weeks that in week 2 we started meandering from what the user really needed. So DevOps enables this rapid feedback cycle. All of the DevOps tools exist for the benefit of the end user, to enable us to get the end user value quickly and get feedback and correct course when we are not giving the user the right thing. So, for instance, we have version control because it enables us to rapidly put out versions where we know if we've made a mistake, we can easily go back to the previous version because everything's under version control. We automate our builds so that builds can be done frequently. The build itself, building the new software, is not error-prone manual process. It's automated. We know we can do it repeatedly, again and again. We automate testing because by automating testing, we know that every time we build software, it's passed through a large test suite. And therefore, we're hopefully not going to generate a situation where operations needs to get paged at 3 a.m. The software passed the whole test suite. It's highly likely it will run in production. We automate deploys. So we need to move something onto the production server. We need automated deployment. That itself should not be a manual, error-prone process. It's something we could repeat as often as we need to. We bring in monitoring. So if we did have any mistakes in our most recent release, our monitoring tools may detect it even before our users do. We can quickly rely on our version control to roll it back and then retest and find out what went wrong. This all exists. I talked about how operations had found releases very painful. One of the DevOps principles was if something hurts, do it repeatedly until it doesn't hurt anymore. So what you do is you keep releasing until you have the release down so well that it's painless.
Yeah, that's how Unix system developed, like continuous feedback from the user.
Yeah. And we get extreme versions of this. We get something like the Netflix Chaos Monkey, and they have a whole suite of chaos tools that deliberately goes around and crashes parts of the system in order to make the system anti-fragile and able to withstand parts of it disappearing in the middle of production. So this has just been a quick introduction to the idea of DevOps, what DevOps is all about, a little historical background, so that hopefully you have an idea of what sort of problems DevOps was an answer to. And that should help you to understand what DevOps is more. Thank you.